Hello students, in this lesson we're going to be learning about how to sketch functions, including how to analyze their various features using various derivative tests. First I wanted to talk about the first and second derivative test. So these are just two different ways to decide whether critical points are maxes, whether they're mins, or whether they're what we'll call saddles, which is neither of the two, where it's like a false critical point in that case. So we're going to look at the first derivative test first. This one employs a chart, which I've kind of already got set up over here. And we're going to use it on two examples so you get the idea. And then we'll just check them with our calculator. But the whole point of this lesson is to be able to sketch curves without referring to a calculator. And this is one of the easier skills on the AP exam, which they love to put in the no calculator section. So you definitely want to master it. You can check things with your calculator. That's all you want to do. And really you should try to just avoid using your calculator as much as possible unless you're curious about a check. We'll check them just to demonstrate the method, but that's about all. Okay, so the first derivative test, like I said, uses a chart to analyze critical points. So the first thing we need to do, of course, is figure out what the critical points are like we did in the last lesson. So of course, if you remember, critical points are where the derivative of f is either 0, producing a horizontal tangent, or where the derivative doesn't exist because of max or min could also occur at like a corner or a cusp. So we've got a nice polynomial function, so I think we only need to figure out where it's equal to 0. So first let's calculate the derivative. So the derivative of x cubed is of course 3x squared using our power rule. The derivative of 3 halves x squared, the 2 is going to come down, cancel this guy, so we'll just be left with 3x to the 1. So there we go, there's our derivative. We'll just set it to 0 because it clearly is not going to be undefined anywhere. So setting it to 0, I can just factor out what they share here. They share 3 and x, and what's left will be x and 1. So now that's factored, so we can see where either factor is 0. This factor is equal to 0, of course, at x equals 0. And this factor is equal to 0 at x equals 1. So we have two critical numbers. So now we're going to put those on our chart to do the first derivative test. So you want to put them in order from smallest to largest so that you don't get confused. So I'm going to put 0 there, give myself a liberal amount of space, and put my other critical number, 1, right there. So now to do the first derivative test, you just need to choose some test points. Because the function can only switch from having a positive to negative derivative at these two numbers. And it may or may not switch sometimes, but these are the only places it could potentially change from positive to negative. So we're going to pick some test values in between them. So I'll pick my test values in red here. So anything over here will work, anything in this entire interval of space, all the way down to negative infinity. So pick something nice and easy, like, I don't know, -2. And then I need to pick anything between 0 and 1. So I'll just go ahead and pick 1/2. It doesn't have to be in the middle because any number in here will tell what the derivative and the original function do for that entire interval because we know it changes only at 0 or 1. It doesn't have to change there. Like I said, it's just potential. So then over here I can pick anything. I could pick 2 again, but just for variety's sake I'm going to pick 3 to show you that it really doesn't matter what test point you choose. So those are my test points. So now where do I need to put them? Well, I need to test them with the first derivative test using the first derivative. That's why it's called the first derivative test. So I'm going to put -2 into the first derivative. Now I can put it in up here, or I can put it into my factored expression. I prefer to use the factors because it's a little easier. So I'm going to keep track of some of these, show my work, and the others I won't. So -2 put into this first factor is going to make -6, but the key is the derivative is negative for that factor. When I put -2 into here, -2 minus 1 will also be negative. That means that the derivative overall there is going to be a positive. And so on my derivative test chart, my first derivative test chart, that means that f prime is positive. That means that the function is increasing in that area from negative infinity up until 0. And now I'm going to put 1/2 in, so 1/2 times 3 is going to be positive. 1/2 minus 1 is going to be negative. So over here, the derivative value overall is negative. That means the function is going to be decreasing in that region of space. Now I'm going to put in my other test point of 3, which I arbitrarily chose, remember, anywhere somewhere in this region to represent it. If I put 3 in, I'm going to get 3 times 3. That's going to be positive. I'm going to get 3 minus 1. That's going to be positive as well. So over here, the derivative is positive. That means the function is increasing. And remember, the idea behind that is that if you have a function over here, f of x, when you have a positive derivative, that means that the tangent line slope there is positive. So you can see that the function's increasing in that area. So remember, that's the idea that we're pursuing, which we've been working with quite a bit. Okay, so we could, of course, use this information to do a very rough sketch of the function. I'll just go ahead and do that. And then maybe we'll check it with our calculator. Well, we'll do the second one first, then we'll check it with our calculator. So at 0, that's where I'm going to switch. So if I have my function over here, I don't know, let me graph the function. Here's y, and here's x. So just a really rough sketch of my function. It's increasing from negative infinity all the way to 0. So that means it'd be, you know what, I'm going to put 0 right here to make more sense. So we'll say that that is the y-axis instead. We'll go and erase this one. Oh, erase this one. There we go. And so my function is supposed to be increasing to that point. I could plug in values to figure out exactly how high it is. We will on another function in a second here. But let's just focus on where it's increasing and decreasing and so forth, because that's what the first derivative test really lets you keep track of. So it's increasing, 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 increasing. And then at 0, it's going to begin decreasing until we get out here to 1. So then it's going to be decreasing. I don't really know how much it is, but then at 1, it's going to be increasing again. So I should get something that looks like that, which you can see is a cubic polynomial. And so you get the idea. So in this first set of examples, you'll see that I'm using really simple algebraic functions, so we can focus on the concept. And then you'll want to definitely watch my next couple videos if you're doing the lesson, because they will involve more complex algebraic calculations and derivative computation. So now let's look at our second function. So first we'll go ahead and compute the derivative. So we're going to have 2/3, leave the inside alone, decrease the power by 1, that'll be negative 1/3, and use our chain rule. So there we go. And now we'll go ahead and simplify it and clean it up a bit. So I think we'll have 4x on top and 3 times the cube root of x squared minus 4 on the bottom. So let's see. It looks like we have a few potential critical numbers in this one. We could get the top equal to 0 if we plug in 0. So there's one critical number. And we could get the bottom equal to 0 if we take this expression and set it equal to 0. So we can divide both sides by 3 and cube both sides in order to get x squared minus 4, which is of course a difference of squares. And so it looks like the bottom produces two critical numbers, 2 and negative 2. So we've got 3 critical numbers to check in this chart. And of course we'll want to do them in order again. So we'll go and put x equals negative 2, x equals 0, and x equals 2 on our chart. We want to pick some test points. So to represent this region, I'm going to pick negative 3. To represent this region, negative 1, 1, and I'll go ahead and pick 4. Remember, you don't have to pick the centers of the regions. Okay, now let's plug those into the first derivative, because that's what this test is, and check them. So when I plug negative 3 in, and I think I'm going to be plugging them in right here, on top I'll get negative. On the bottom, when I put negative 3 into squared, I'm going to get positive. And it's going to be 9, so of course we'll avoid getting an imaginary number. So it's going to be positive. So overall down here it's negative, meaning g as a function is decreasing in that region. Okay, at negative 1, when I plug it in on top, again I'm going to have negative. When I plug it in bottom, I'm going to get, I forgot this is a cube root, so I totally don't have to even worry about imaginary numbers. That's good. So when I plug it in the bottom, right here, right, I'm going to get negative 1 squared minus 4. That's going to be negative. Cube root's going to leave a negative number negative. I won't worry about imaginary numbers. So we're going to have a negative on the bottom. And if you need to show more scratch work, please do. This is about the amount of work that I think you usually need to work with. So that means the function is going to be increasing in that region. 1, our representative between 0 and 2, on top is going to be positive. And when I put it in the bottom, it's going to do the same thing the other negative one did. So here I'll have negative, which means the function is going to be decreasing. 4 is going to, I think, yield positive on both, so pretty easy there. And there you go. I want to point out that up here, where it's alternating, there's no reason that it has to alternate like this. Some functions will do that, some won't. And in order to think about sketching this function, which I'm not going to do this time, let's go ahead and just think about what's happening at each individual critical point. This one came from the bottom, so remember this is kind of going to be a cusp on the function, or a corner. 0 came from the top, so I'm thinking this is going to be kind of like more of a maximum. And you can see that that also helps you visualize what's happening. It's going up, then it's going down. This is going to be a max. This one's going down and then going up, so this one's going to be a min with a cusp shape. And then over here, 2 also came from the bottom, so this is again going to be a cusp minimum. Okay, so I can go ahead and draw that. Let's just go ahead and check that one with our calculator. So I'll bring that one up here just quickly, and we'll check to see if that confirms what the function actually looks like. So I'm going to go to y equals and clear out what I had previously, and just plug this function in and see if it looks right. So I've got x squared and minus 4, and we'll raise that to the 2/3 power. And we'll go ahead and zoom standard and see if it looks about correct. So if we go over here to our chart, I think we'll see that it basically looks correct if we think about it matches our chart's information. First, the function's decreasing till about -2. It's got a cusp minimum at -2. Then it's increasing until about 0. Then there's a little maximum. It's decreasing again, and then it hits another cusp minimum before it continues increasing. So you can see that without even using my calculator, I pretty much already had a nice picture of it. I just need to plug in those numbers or a few other numbers to get some y values to nail down exactly where it's at. Okay, so let's think about using the second derivative test now. So the second derivative test is another way to do the exact same thing. It's a way to decide whether a critical point is a max, min, or a saddle. It's just another option. The idea is that sometimes it's better when you can easily compute f prime of x, as you'll see this example is good at, or when it's really hard to plug into f prime, which those other two weren't, but some functions are. A lot of the time also the AP exam will force you to use the second derivative based on the information available, so it's really important to be able to use this test. And I think you'll like it. It's a little bit more succinct. So first, we need to compute the second derivative and the critical numbers. So we'll start with the first derivative, which for this function is going to be very simple. So here we go with our first derivative according to the power down rule. And then we'll compute the second derivative because we're going to use that for the test. So that's going to be -60x cubed and 30x it looks like. So now I need to figure out what I'm testing, so I'm going to figure out what the critical numbers are. To do that, I'll set this equal to 0. So when I set that equal to 0, I can do it over here. I think I can factor out a 15 and an x squared. I'm just going to pull out a -15x squared. So when I do that, the first term will leave x squared, and then the second term will just be -1. So there we go. That gives me my critical numbers if I factor this second factor with difference of squares. All right, so there we go. So our critical numbers here are going to be 0 makes the first factor 0, 1 makes the second factor 0, and -1 makes the third factor 0. So those are my critical numbers. I'm not going to draw a chart this time to test them, like the first derivative test. I'm going to use my second derivative. What I'm going to do is I'm going to plug each one into it. So I'm going to say, okay, k double prime of 0 is going to be, I'm plugging it in right over here. So -60 times 0 cubed plus 30 times 0, which of course is going to be 0. I'll tell you what these mean in a moment. Let's just plug them in first. So we're going to plug in 1, so -60, 1 cubed is 1, just going to simplify, and 30 times 1. So that's going to be basically 30 minus 60, which is -30. And we'll plug in our last critical number before we interpret them. So when I plug that one in, I get -60, -1 cubed produces a -1, of course, and 30 times -1. So that's going to be what? Let's do some simplifying. 60 minus 30, so that's going to be positive 30. Okay, so what does each one of these mean? So I'm going to start with -1 here. So -1, when I plugged it into the second derivative, I got a value of positive 30. This one over here is positive. So if I think about it, we know that it's a critical number. That means it could either look like this as a minimum or like this as a maximum. And of course it could be cuspy instead, but it's basically the same idea. So, and it really can't be cuspy, I guess. I misspoke, because if it was cuspy, then the second derivative you couldn't calculate at that point. It wouldn't be differentiable there. So it's got to be nice and smooth like one of these. So anyway, it's got to be one of those two things. So this guy over here is what we call concave up, and this guy over here is what we call concave down. So this is like the concavity. I like to think of an upward facing cup shape or a downward facing cup shape. So when I calculated the second derivative of -1 and got a positive 30, then that means it's going to be concave up because it was positive. So at -1, the value looks like this at -1. So that's concave up. So since it's concave up, that tells you clearly, looking at this picture, that this guy is a minimum. So I can say that this guy is a local min. Okay, so now let's check 1. 1, we got -30. So if we think about the picture there, then that means that the second derivative's value is negative, which means it's concave down at that x value of 1. So that's what it's going to look like in that local region. So you can clearly see from the picture, since it's concave down, that's going to be a local maximum. And 0, since we got a value of 0, it's neither concave up or down. That's really going to look like this. It's going to be something like what happens with the x cubed function. So that's what's happening here. It's neither up or down. So this guy is going to be what we call a saddle. And I think you'll understand why it's called a saddle, because this kind of looks like the saddle you'd put on a horse or something like that. It's neither a max nor a min, but the slope of the tangent line was, of course, instantaneously 0 for just a second. And so that can happen as well. So that's the second derivative test. Notice no chart was used to decide whether they were maxes, mins, or saddles. We're just visualizing concave up, concave down, or whether it looks like a saddle to decide whether it's a max, a min, or neither. So sometimes that's a lot easier way to do things. So let's kind of use what we think is best on this final problem. And we're also going to talk about the concavity test. So the concavity test also uses the second derivative, but it's not the second derivative test. Make sure you don't confuse them. Think of it as a third test. This one is going to allow you to find an inflection point and then track what that inflection point does. So an inflection point is where you change concavity. So let's write that right here. Change in concavity. It's where the concavity of a graph changes from positive to negative or vice versa. So first let's compute the derivatives here. So we'll take h prime and figure out what that is, which for this function is nice and easy. Make sure you watch those second videos, which show you some more involved computation. So there's h prime. Let's go ahead and just take the second derivative as well. So here's h double prime. And so we'll go ahead and find the critical numbers and the inflection points first. So we'll set this polynomial equal to 0, excuse me, to find the critical numbers. So you could go ahead and factor this guy. It looks like they share a 3, so I'm going to pull that out. That'll be the easiest way, I think. So minus 6, right? And minus plus 9. Ah, is that a perfect square trinomial? I believe so. Yeah, so it's x minus 3 quantity squared. Sweet. So that means the only critical number is going to be at 3. That's good. Let's also find the inflection points now. So let's label that as a critical point. And inflection points are going to be where the second derivative is equal to 0. So pretty simple. So here we go. And we'll add 18 to this side, and we'll get 3. So that guy is an inflection point. So now let's put all of our information together and sketch the curve. That's the ultimate goal of this section. Oops. Yeah, that's fine, I guess. So let's see what we've got. So we'll do our first derivative test to check the first one. I think we've got the second derivative easily, so maybe that would be more efficient, but I've got the charts lined up here already, so let's go ahead and just put them on there. So we only had one critical number, so we'll just put that right in the middle at 3. And we also only had one inflection point, which also turned out to be 3, crazily enough. So let's plug in 3 to the first derivative, and you can see that it's really key how you label these charts. So the first derivative test, we're going to plug it in and see what happens. So just like last time, I need to pick a representative point, maybe 1, and maybe 6. I don't know. So if I plug 1 into the first derivative, I can plug it in up here, remember? Or I can plug it into the factored expression down here, which I prefer to do. So if I plug it in there, I'll get 1 minus 3 is negative, and then I'll get 1 minus 3 is negative, and then I've got a 3 outside. But basically the idea is it's going to be positive over there. So the function h is increasing. When I plug in 6, it's going to be 6 minus 3, 6 minus 3, so it's going to be this. And so, again, the function is going to be increasing. Well, that means that this is neither a max nor a min. It looks like this guy was a saddle. Okay? You can just look at the shape of your arrows to help make that determination. So now let's go ahead and use the concavity test. This is not the second derivative test. Remember, we didn't use a chart to do that. We just thought about the shape. The concavity test is, again, going to use a chart and the second derivative. So we found that the inflection point also turned out to be 3. So let's go ahead and pick some values. I'm just going to pick the same ones for simplicity's sake. But this time we'll be plugging them into the second derivative. So make sure you label your charts. If you don't, they're really meaningless, and you get penalized a lot for that. And also, of course, you'll lose track of what they mean. So when I plug 1 into the second derivative, I'm going to get 6 times 1 minus 18, which of course is 6 minus 18, which is negative. So this is negative. So that means h is concave down. When I plug in 6, I'm going to get 6 times 6 minus 18, which is 36 minus 18, which is going to be positive, which means it's concave up. So thinking about what my information is, let's see if we can just draw, and then we'll check our answer before we leave off for this video. So we know that the interesting information all kind of happens at 3, right? Let's also plug in some values just so we can get a pretty complete sketch of this curve like you'll need to do for several problems in the assignment and on the AP exam. So when I plug in 0 to function h up here, what do I get? This goes away, this goes away, this goes away. So my x and y intercept look like they're both 0. Then we knew at 3 that there's a saddle point, so we know it's got to go like this. And we know that that's also an inflection point. So let's kind of think about this. So it's supposed to increase up until 3. So maybe I'll be increasing. Oh, and also it's supposed to be increasing, and like this says right here, concave down. So it's supposed to be increasing, and I'll try to draw a concave down shape. And then at 3, it changes to concave up, but stays increasing. So now it's going to change to concave up, but stay increasing like that. And so I think you can see how this guy right here is a saddle where the tangent line is momentarily 0, but it's also an inflection point because it changes from having this kind of shape right here to having this up kind of shape. So that shows that it's an inflection point, also a critical point. Let's just check our work before we leave and have a look at it on our calculator. So I think we have a pretty good graph of it. We just have to check it. And you don't have to check all of yours. You should really be trying to operate on this assignment without your calculator. And so it's a little hard to see there. Maybe I will make my window go a little bit higher, maybe 100 by 10s. Let's try that. And there you go. You can see the same kind of shape that we had right there. And you can see that it also matches all the information from our first derivative test and our concavity test, not to be confused with the second derivative alternative to the first derivative test. So I hope that made sketching curves clear and also made you a little bit more competent with the increasing, decreasing issue in calculus, and we introduced the issue of concavity. I'll see you next time.